Alright, in section 2 we're going to look at more operations involving vectors. In this section we're going to look at the scalar product, or what we call the dot product. Now when two vectors undergo scalar product, for example if I have two vectors A and B, the scalar product of A and B is denoted by A dot B. This is also known as the dot product. The definition of dot product is when I take two vectors A dot B, it is actually equals to the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. So theta is the angle between the two vectors A and B. B is the magnitude of the vector B and A is the magnitude of vector A. So if you look at this definition of the dot product, you realize that A magnitude, B magnitude, cosine theta is also a value. So the right hand side here is actually a scalar. Based on the definition of the dot product, when we take two vectors and then we do a dot product between them, the result is always a scalar. Something to note about is that the theta can only take the angle between 0 and 180 degrees, and this was covered before. Angle between two vectors is measured when the two vectors are pointing away from the same point or they are pointing towards the same point. Question: can A dot B be negative? The answer to this question actually lies on the definition itself. If we were to look at the expression on the right hand side, the modulus of A and the modulus of B are both positive numbers. Cosine theta, however, depends on theta, the angle between the two vectors. As we have discussed just now, theta can be either acute or obtuse. So in the case where theta is obtuse, cosine theta is actually less than 0, and thus the right hand side is negative. So it is possible that A dot B to be negative. So how about the scalar or dot product applied to the base vectors I, j and k? What would the theta be? Remember, I is parallel to the x-axis, j is parallel to the y-axis, and k is parallel to the z-axis. And x, y and z-axis are all perpendicular to each other. So theta is actually 90 degrees, right? So when theta is 90 degrees, cosine 90 is actually 0, right? So therefore A dot B will get you 0. We will cover this later. Some of the properties of a scalar product is that the scalar product is commutative. The reason it's commutative is observable from the definition of the scalar product itself. When we do the dot product between A and B, by definition we have the modulus of A times the modulus of B times cosine theta. Now since all these items are all scalars, they can be switched. When you switch it like this, it actually gives you the formula for B dot A. So that means scalar product or dot product is commutative. Consequently, we can also see that they follow the distributive law, and also the scalar multiple of vectors applies accordingly as well. Now what happens when we take the vector A and we do a dot product with itself? The result is that we have the magnitude of A squared. What is the reason behind this? Again, if we apply the definition of scalar product, if we take the vector A, we dot with itself, by definition, we have the magnitude of A times the magnitude of A and times the angle between A and A. The angle between A and A is actually 0 degrees, and this will give you 1, and therefore you have modulus of A squared. Alright, so consequently, if you take the base vector I dot with itself, J dot with itself, K dot with itself, we will actually get 1. The reason being I dot I will give you magnitude of I squared, and we know that magnitude of I is 1 because it is a unit vector. Similarly for J dot J, and k dot k. Now perpendicular vectors. If A and B are perpendicular and non-zero vectors, then if we take the dot product between the two vectors A and B, then if we take the scalar product of the two vectors, that is A dot B, we will actually get the zero scalar. Now if A dot B is equal to 0, then it is either A is the zero vector, or B is the zero vector, or A and B are perpendiculars. So when we have a result where A dot B equals to 0, there are three possibilities. So similarly for the base vector, since I and j are perpendicular to each other, j and k are perpendicular to each other, k and I are perpendicular to each other, when you dot them, you should get the zero scalar. Now one very important thing that you should note is there is no such thing as division of vectors. So if I give you a relationship between vectors A dot B equal to C dot D, it does not imply that B can be cross multiplied such that C dot D divided by B. This is not true at all. Now how does the scalar product of two column vectors look like? Now if I have two column vectors A1, A2, A3 dot with another column vector B1, B2, B3, the result is simply multiply the 2x component plus multiply the 2y components plus multiply the z component. As mentioned before, A dot B is a scalar, actual real value number. Then there is no such thing where the operation looks like this. This one has no meaning. The reason being A dot B, by the definition of the dot product, A dot B is already a scalar. So if you were to write this, you are actually saying that a scalar dot with another vector. For example, you are saying that 2, the number scalar, dot with another vector. This one has no meaning at all. So in order for you to actually take a scalar with and multiply it to the another vector, you simply just need to do scalar multiple of a vector, which is basically 2c, right? Which is what we should write here instead. Now if given that A is a zero vector or B is a zero vector, then the dot product between the two of them will give us the zero scalar. Alright, I will leave example 13 for you to do it on your own. We will go into example 14. Now in example 14, you are asked to find the possible values of lambda such that these two vectors are perpendicular vectors. Now 3i plus lambda j, we can write it in the column form. 2 lambda squared I minus j, we can also write it in column form. To find the values of lambda such that these two vectors are perpendicular, we apply the condition where when two vectors are perpendicular, the dot product between the two vectors will give rise to 0 scalar. So what we will do is 3 lambda dot with 2 lambda squared negative 1, we should get 0. Simplifying, you have 3 times 2 lambda squared plus lambda times negative 1 equals to 0. Solving this, where you actually have 6 lambda squared minus lambda equals to 0, will give you the values that we are looking for down here. In example 15, we are asked to express the dot product between this vector and this vector, this vector and this vector. In part A, we are asked to do a dot product between 2a plus 3b and itself 2a plus 3b. So basically what you're going to do is do a dot product term by term. So we're going to take 2a dot with 2a, 2a dot with 3b, and then 3b dot with 2a, 3b dot with 3b. This can be simplified to 4a modulus squared plus 6a dot b plus 6a dot b plus 3b modulus squared. And therefore we have 4 modulus of a squared plus 12a dot b plus 3 modulus of b squared. So that will be our final answer. Do take note that a dot b, this is actually initially b dot a, but because we know that dot product is commutative, it is equivalent to a dot b. Alright, I will leave example 16 for you to do it yourself. Let's take a look at example 17. Now in example 17, you are given a diagram, a triangle ABC with the vectors BA as defined as C, CB defined as A, and CA defined as B. In part A, you're supposed to find C in terms of AB. Part 2, you're supposed to find the dot product of C with itself in terms of AB and A dot B. And then based on what results that you found in part A and part B, you're supposed to obtain the cosine rule. And from secondary school, the cosine rule is that this length squared is equals to this length squared plus this length squared minus 2 times this length times this length and the angle in between, the cosine of the angle in between. Alright, so let's take a look at how we can find the vector C first. Now the vector C is this, so you can actually do a triangle law. Okay, so by using the triangle law, we can see that A plus C is equals to B. Alright, so therefore C must be equals to B minus A. Alright, so that is quite easy to find. Now now what is C dot C? So based on what we have found in terms of what is C, so C dot C is basically B minus A dot with B minus A. And this one, if we were to do it term by term, or we can actually expand it using our quadratic formula, because we know that A dot B and B dot A is commutative, so they are actually equal. So we would have B dot B minus 2A dot B plus A dot A. Alright, and hence we can actually find the relationship in terms of B squared and in terms of A squared and in terms of AB. Alright, okay, so because of this, right, we can actually see the cosine rule coming out already. Right, so based on this equation, C dot C is in fact C squared, so in the end we can actually have the cosine rule emerging.